This is a schematic of a quantum computer, and this is exactly what the problem we have now. You look at this so-called quantum computer, although you have a tiny qubit here, all of these are just classical equipment. And that's why I always say that E students are very suitable to work in the quantum computing industry, at least at this stage. But even in the future, if we can integrate them, it's all about IC, classical IC, right? Of course, all these things, when you go to low temperature, you will talk about quantum noise, right? The physics people will chime in, right? They know all those complicated theory, open system or whatever, right? But we can do a lot of things in this at this level. So on top of here is a controlling system. It's just basically a FPGA or a high performance server. This is a company called Quantum Machines. They provide this type of controlling system. And what it does is this, it tries to generate some signal. This signal is maybe a pulse, very simple, just a pulse. What you get from Keysight or other equipment company, use it to generate a pulse. This pulse is going to be mixed up. You see this is a mixer, right? A mixer go through a local oscillator, right, for those RF people. Then you bring it up to the right frequency. You then send it to here, right? And then you are at the 300 Kelvin, right? Because this equipment are bulky. You cannot run them at, what is the temperature here? 10 millikelvin. You even don't have the dilution refrigerator that has the power to take away those such a lot of that much of energy from the system, right? So at this moment you cannot co-integrate. Even I allow you to make them on a chip, you just don't have the dilution refrigerator to take about 100 watts of power. You cannot do that. So once we send the signal, what do? We actually have a fairly large signal. We try to make it large. And then we will attenuate it through some attenuator. Minus 20 dB, minus 20 dB from 300 Kelvin to 4 Kelvin, 4 Kelvin to 700 millikelvin, and then to 10 millikelvin. We kept attenuating. Why? Because we want to reduce the noise from the room temperature. All your signal all get the thermal noise at 300 Kelvin. And we need to reduce them so that they are lower than quantum noise when they reach this qubit, right? And this is like we have this large signal, so our signal is still appreciable. In this particular example, you see that I send a pulse which is negative 47 dBm, right? What is dBm? It's just the power you compare to 1 millivolt, right? It takes 20 log, right? If you forgot about this, this is the dBm, right? It's just like you take, if it's, you have a voltage, right? You just take the log of the V square, not V square because I already take 20. So actually I better just call it 10 dB. 10, right? 10, and then whatever power you have, right, divided by 1 milliwatt, right? And then the units is in dB. I should not say this is 1 dB, right? The unit is in dB. Is that okay? Right? So that is the attenuation, right? I mean the dBm, the power that you have, right? So it's a very low power, right? It's even less than 1 millivolt. Once you go to here, you attenuate it to negative 123 dBm. In this frequency we're working on, I forgot what is it, about 5 gigahertz or 6 gigahertz. It's only 363 photons, right? It's countable. Number of photons is countable. And of course, we want to make it even smaller. But no matter what, after this, what it does is that it's going to go through a resonator. This resonator is coupled with the qubit. The qubit can be at 1 state or 0 state. And whether it is at 1 or 0 states, it's going to affect the resonant frequency of this resonator. Right? And because the frequency is changed, then we have different reflection or transmission coefficient. as you know from the RF, right? You shoot a pulse to a resonator. If you have a different frequency, then you will have different transmission spectrum, right? You have going to peak at a certain frequency. And then this one is going to go through here. We go through a quantum amplifier. And then you go for a HEMT, high electron mobility transistor. This is no noise amplifier. And then you go through the amplifier, regular room temperature amplifier. And then you try to read at what frequency it transmits well. Then you know that what is the effective resonance frequency of this system. And from there, it deduces whether the qubit is at 0 or 1. So that is the reading mechanism of a quantum computer. And of course, we also have the driving. Actually, I forgot which one is the read. Actually, I think I forgot which one is right. But anyway, one of them is to do the manipulation and reset, including I can send a pulse to here. Again, I have another circuit. This circuit is going to make the qubit evolve its state, right? As we discussed last time, what is a quantum gate? It is just a pulse, right? You just send a pulse to the qubit and then its state will change, right? We are still not familiar with the superconductor qubit yet. Just maybe think about a spin. The electron was spinning up. Now I apply a pulse, maybe an AC magnetic field, and then you will start to precess around, and then it will point another direction. And that's how you get a different state. Instead of 0, it becomes alpha 0 plus alpha 1. Okay? Now, so this is just a big picture, and after this class, I hope that we understand what it is, right? So in this particular paper, what we are trying to say is, now, how should you send out the pulse? If I send out a very long pulse, definitely it's good. You help me to increase the resolution. But then the reading time is very long. This is not good, right? If you take a long time to read, maybe even before you finish the reading, your qubit already have decoherence, right? So that is a limitation for today's quantum computer. They have a short decoherence time. In this particular case, it's about 250 or 300 microseconds. So if you want to do some operation on the qubit, you better to have your operation maybe in the order of 1 microsecond or hundreds of nanoseconds, so you can have 1,000 or hundreds of operation NAND gate or gate before it die, right? And then you redo the system, right? That is one thing. Another is the energy, right? If I apply more energy, of course it is good, but that may cause other problems like heating up, or it can cause we can even modify the qubit state if the energy is too high, right? So all this read out depends on also the noise. Think about that. I'm talking about you read it by seeing at which frequency it transmits through. But if I have a lot of noise, you won't be able to distinguish, right? So that's what this is doing. Can we develop a framework just to understand the trade-off between the pulse width, pulse energy, resonator quality, or etc.? Is that clear? The picture? This is just an overall picture. Okay? So in this case, right, in their lab, they use a superconducting qubit. There are different types of superconducting qubit. One of the most common one is called Transmon. So what does it mean? Look at this one. This is a so-called Josephson junction. So, or actually, when we draw in this way, it actually become a Transmon already. But anyway, so this is like a Josephson junction, right? Just what is a Josephson junction? You will learn more later, but basically it's just a capacitor. You have the maybe niobium. What's the NB? I forgot this. Niobium as the metal. And then here you have aluminum oxide. Okay, and it is under 10 Kelvin, niobium become a superconductor. So you have a superconductor, insulator, superconductor, just like a capacitor, right? But it has something very special called Josephson effect we will discuss in the future. But anyway, at the superconductor, all the electron pair up. You don't have single electron. If you have single electron, that's a problem. We call it quasi-particle. They pair up, they have opposite momentum, opposite spin, and they have spin equal to 0 because one is up, one is spin down, right? So they have integral number of spin. We discuss later, and they are no longer fermion. They don't obey the Pauli exclusion principle. They become boson, just like the light. That you can have many particles occupying the identical state. No more Pauli exclusion principle, right? But anyway, because of this, they can form as an ensemble, like what they call Bose-Einstein condensate, right? So there's just like an army, all of them moving in coherency, like the laser, all the photons moving coherently. They share the same quantum state, right? But anyway, so now you have this Josephson junction. We put a capacitor here. This is called a superconducting island, right? Because this is capacitor. This, in some sense, is also a capacitor, right? So in this island, you can have 1 or 0 excess pair of Cooper pair, n equal to 0 or n equal to 1, right? You just set up the stage, DC bias. Maybe you have already a background charge. Now, by biasing it differently, you can inject 0 extra Cooper pair or 1 extra Cooper pair. That's okay, right? Just like you instruct 1 extra electron or 0 extra electron. But because they're quantum object, right? I just told you they just a huge quantum object, a Cooper pair. They can be in a superposition if you do it well. We will go to the math later, right? Why we can achieve this. But you just trust me. You just like, it has that much percentage of a possibility at 0 and that much at 1, right? And by the way, do you remember what is the probability of having n equal to 1 for this wave function? What is the probability? So I have two states, right? A linear superposition of 0 and 1, right? If I measure it, what's the probability I will get 0? Alpha square. The magnitude of alpha square. Yeah, good. And then 1 is beta square, right? What is Transmon? Transmon is basically just like a regular, what we call the Cooper pair box, where, right, this is called the so-called CPB. Right, this is a box in which we can put a Cooper pairs, but we just add very large resistance, very large shunting capacitor. So what is the goal, right? We don't really understand this figure at this moment. We will learn it. But basically, here on the x-axis is talking about something called the background charge, Ng. I just told you that before we put any extra electron or Cooper pairs, you should already have a background charge, right? Depends on your setup. You see that it has 3 states. Here shows you the energy. This is the ground state. If you have different background charge, you actually have different ground state energy. This is the second state, just like the atom, right? In an atom, you have the ground state, the s orbital, and then p orbital, right? So this is the second state. This one is the first state. The problem is, you see that this is the ground state, which means 0. And this is the upper state. If I have some background charge, the ground state and upper state will change a lot. And the biggest thing that if I have some noise, what we call the charge noise, that you cannot avoid because your environment gives you a lot of noise and then also other issue, right? Then you are going to have a big fluctuation between the energy of the ground state and the first state. Is this okay? Because Eg is the background charge. So what Transmon did is that it tried to make this really fat by having a very much larger, what we call Josephson junction energy over the charging energy, which we will discuss in the future also. Then you will see that even I have the noise, the distance between the first level and the second level will be the same. Then I don't care about the noise, right? It just like, yeah, no more analogy, just, does that make sense to you? Okay, maybe you don't see what I'm, oh, yeah.
So do these energy levels correspond to the 0 and 1 states?
Yes. So
the ground state be 0, and then the first excited state
is 1, yeah. Okay. Okay, a very vague understanding, no problem, right? I won't be understand neither if it's the first time to see this, right? But we start going into here, right? I'm not going to test this here until I teach you again the details, how to derive this in the future, okay? Anyway, so then what does a Transmon qubit look like, right? This is the one they fabricated. Now look at this. This is the Josephson junction. And in this particular case, actually, they use aluminum as the metal instead of niobium. Okay. Again, they have this aluminum oxide as the insulator. This is an IC chip, just what you do for your whatever TSMC 65 nanometer tape out, right? But this is for superconducting. So instead having the regular aluminum layer, right? Or even the silicon layer with ion implantation, with N-well, P-well, with poly, with OD, you actually just, usually it is very simple. You just have this metal. In this case, they use tantalum. Yeah.
Is this a top-down view or
top-down?
Section?
Thank you. So here, this is the top-down. You put the wafer on the table, you look down, yeah, and this is the magnification, and this is the part of this one. Do you see this one? Yeah, and this is a capacitor, isn't that? It's just connecting from one terminal of the Josephson junction to another terminal, right? That is what this is doing. And that's how you get the Transmon qubit, because this is a huge capacitor. So the qubit itself just sitting over there, and with this Transmon, with this capacitor, and it coupled to the outside world just full of capacitor, this CG, okay? And there is a quantum computer. Very simple compared to your NMOS and PMOS you learn in 128 or 221. Yeah. Sorry, this is not clear. Sapphire has the same color, so all this gray one a sapphire. When I say this aluminum, this one is talking about this whole structure. Correct. Tantalum, aluminum, and then there is a junction. You see this king, which is aluminum oxide, and then aluminum again, and then tantalum. Yeah, good question, right? And then this is a modeling of it, Josephson junction, and then a big capacitor, and then we have a resonator, because we are using this one to probe it. So it will shine, you will send a microwave pulse to here, and then it's going to refract. And at which frequency it refracts the most depends on the resonant frequency of the system, right? But this resonant frequency depends on the qubit itself, whether the qubit is spin up or spin down. I mean, in this case, whether it's 0 or 1, right? Then you know whether it is 0 or 1. This is the way you measure the quantum computer qubit. Right? So up to now, you don't need any quantum mechanics. All you're doing is just what you learn in the EM and microwave. Okay? Now, of course, if you want to go to detail, you need quantum mechanics, right? But here, again, you won't understand. It's a very sophisticated. I just want to simply say one thing. This is very interesting, and we only need to learn one formalism. We probably can understand many things. This is something what they call quantum electrodynamic cavity QED, right? In the physics, right? They call it AMO, right? Atomic molecular optics. This is an atom, a real atom. it has a ground state and an excited state. And you put it in an optical cavity, and then shine some laser light to it, right? The cavity itself, the cavity itself will have different energy level, meaning that whether it has 1 photon, 2 photon, or 3 photon, right? But then the energy level, the total system, also depends on this atom, whether it's in ground state or excited state, right? For example, whether it's in S or P, for example. The example I'm giving might be wrong. And then they will couple to each other, right? So you see there are some mechanism that happen in the qubit also. The atom might excite a photon to the cavity and then go back to ground state, or absorb a photon, right? It excited, then the cavity lose a photon, right? The cavity itself can lose energy to the outside world, and the atom itself can lose energy to other path. Okay, so there are many important figures of merit. For example, the resonant frequency of the cavity, the atomic transition frequency, right? Which means what is the energy that I need to bring it from ground state to excited state. And there's a coupling G between the atom and the cavity. Okay, so we won't go into details, right? But why I want to mention this, it turned out that our circuit is like that. We call it circuit QED. The formalism is the same. And we call this Transmon, this superconducting qubit, is an artificial atom. Isn't that we say that it can have 2 states? 0 excess Cooper pair, 1 excess Cooper pair. It's just 2 energy level like the atom. So what we are really doing in many quantum computing situations is to make an artificial atom. This is not really an atom physically, but it behaves like an atom when we put inside this cavity. This is the transmission line. Many of you know, but if you don't know, doesn't matter, right? You have the ground outside, maybe coplanar waveguide. I don't know exactly what it is. And then you cut it, here it becomes a cavity, right? And you know all this cavity, your solution need to have this is not grounded, so you have the maximum, antinode at the end, just like the string, right? And they couple capacitively to the outside world. This cavity will talk to this qubit just through coupling, through the capacitor. And it is like the G we study here. The atom will couple to the optical cavity through some mechanism. If you trust that, I think it's not difficult to understand that the atom can interact with the cavity, right? The atom can lose the energy, like it emit the lights go to the cavity, or absorb the lights, then you excite the electron, right? This is something like this. But now all of them are photon. Now this is concept sometimes electrical engineer always feel confused. Suddenly, I didn't realize that. What we are doing are all photon. Microwave are photon. Remember, because all we are working is just under the Maxwell equation. They are all electromagnetic field, right? So although they are not visible lights, but what we are dealing with in our circuit, they are all photons. So sometimes they call it photon. Do not get confused and keep thinking, what color it is, right? It's just a very long wavelength photon for microwave, right? So it has this different path. I won't go into detail, but the point is you can start with no photon, with no microwave, right? You don't capture anything in this cavity, just like the optical cavity. No photon, and then no extra charge in the transmon. And now I shoot a microwave pulse. It will be able to go to accept 1 photon, then your cavity is storing 1 photon, but you do nothing to your charge. You are still at your ground state. Okay? And this one requires this much of energy in order to go from this state to this stage. You also may have 1 charge, means you are in state 1 and no photon there. You shoot a microwave, then you will go to 1 photon and also the charge at 1. So you gain an extra photon in this cavity. But you see that the energy to go from here to here is different from here to here. The difference is 2g squared divided by delta. G is the coupling, how strong the atom coupled to the cavity. And delta, I failed to mention, is the difference between the resonance frequency of the qubit or the artificial atom and the cavity, right? So delta is what we call the detuning. Your cavity has a resonant frequency, and your atom also have another frequency. We can make them the same, then detuning is 0. We make them different, a little bit different, then we get some detuning, right? And this is important in the engineering, right? So if you make the detuning smaller, you can separate them, separate the two frequency quite a lot. Now, the only thing I want you to, yeah.
What does it mean by suppressed?
Suppress is just it has the possibility to go here, but due to other reasons, this one will not happen. Okay. Yeah, so you can ignore this for now.
Because I was going to ask these other excited states, but those are suppressed.
Yeah, due to the setup. And actually, if you ask me now, I forgot the exact reason. This paper did explain it. Yeah. So that's a good point, right? He is saying that you can go here and you also can go here. Why it will choose to go here, right? Yeah.
What determines the polarity? Is it the delta?
Polarity of what?
Like the minus and the plus g squared?
Oh, this is just, this determined because of this transition level. This will transition to here, so this need to be add more, okay, I see what you mean. Why this become minus g squared or plus g squared, right? That is because of the detuning. If you don't have this just detuning, then you will then they will all shift together. You just go through the math. I cannot show you now. I failed to do that. But because of this detuning, right, you will see that instead of this solid line, you will go to this dotted line. Yeah. So
it depends on the frequency?
Depends on the system.
Okay.
Yeah. It will be plus and minus anyway, right? But by how much, then that depends on G and delta. Yeah. Okay, anyway, maybe if I did not explain well, what you really want to take home is, first, I want you to recognize that microwave is just photon, right? So if you have been feeling confused by this. Second, all this what we are doing is just an artificial atom coupling or interacting with a cavity. And our goal is that we know that there are different states in this system. If it starts with 0 for the transmon, we need a different energy to excite it compare if it starts with a 1 state. Okay, and that is how we distinguish them. This G squared over delta is a very important term that you need to optimize in your project, Crosscut. It basically is telling us that how much this resonant frequency is going to change due to your qubit is at different states. Right? So now you just ask me how you determine plus minus. If there's no plus minus, if these two terms are 0, I cannot distinguish them because omega R can bring this to here. It also can bring this to here. So if I start from 0, I see all the absorption. If you start from 1, I also see absorption at the same frequency. I cannot distinguish it. But with this G squared divided by delta, now they split, right? So if it's your qubit as 0, it will absorb maybe at lower frequency. Your qubit as 1, it absorbs at higher frequency. And then I can distinguish. So this is the crosscut, which is very important. We say how much the cavity resonant frequency, the capital omega, is pulled by it, right? Due to the coupling. So that's all I want to say for this part, okay? Now then, yeah.
What is the unit for G?
The unit for G, I think, that's a good question, I forgot. What is the unit for G? Maybe unitless, I guess. Let's see. I need to check. I'm sorry. I don't know. What is the unit for G? Okay. So, but you see that eventually, right? This is omega, right? Omega. So this one need to be omega. And then this is unitless, racing operator. It probably is not unitless, but I need to check. Yeah, because we're missing one A. Yeah. Okay, so now we understand, all we note is that, hey, to measure the qubit looks like it's easy. It's just because the qubit at different stage, and then it changed the system I'm measuring, right? And then I know what state it is. So it becomes just purely classical. Now, so for example, now we know that if I shoot a pulse to this system, because the qubit is at different stage, I have different transmission frequency. Spectrum, right? So for example, when the state is at 0, it will peak at here. When the state at 1, it will peak at here. So when I'm going to measure it, I'm going to measure this point. Now this is the total magnitude. It should have the imaginary and the real part. So if I try to distinguish the imaginary and the real part, then I will see the difference. How do I do that? Let me just quickly talk about. Then how do we do the simulation? Crosscut, it can come from your experiment, right? You know that with this qubit and this resonant cavity, how is it going to change the resonant frequency of the cavity? You also can do it through something called energy participation ratio simulation, which you will do in the project. And then what we're doing here is just that we know what is the crosscut. We did not really simulate the qubit. What we did is that if the qubit is 0, I assume that I have a little bit longer cavity. When it is one a little bit shorter, then it's going to have different resonant frequency, right? Because the cavity changed. And then we use this one to figure out HFSS to figure out what is the S2-1. What is the transmission spectrum? And that represents what we will get, right? We get the S2-1. Then we apply the pulse, and then add the noise. The noise comes from the amplifier, comes from the environment. And then we measure the real and imaginary part. Now, that's why I want to show you on the right. They have different transmission spectrum and different amplitude. I want to measure at this point. Then you will say useless, right? Because they are the same. How can I distinguish? But however, if you look into the real and imaginary part, you will see they are very different at the midpoint, 7.252, right? For example, at this point, this real is so different from this real, although when the imaginary are the same. And again, you can shift a little bit to decide which one to pick. Now, so if I shoot a pulse to it, it will give me different combination of real and imaginary. I can plot this. I will just directly go ahead. This is how to calculate the noise. This is not important for this class at this moment. Right here, I just want to show you the simulation. You have different real and imaginary, and then we add the noise. And you can imagine if the noise is super large, I cannot distinguish them, right? Yeah.
Could you go back to the slide with the suppressed stuff on it?
It
just said suppressed on the diagram.
This one?
So it looks like we're dealing with 2 qubits. You have 0, 0, 0, 1, 1, 1, 0. But
no.
We're saying that that's so.
No, 1 qubit. This is the state of the cavity. We're saying that we have 1 photon. And what we are really using, it is the transmon here as the qubit. So if I have a bigger quantum computer, I will have this qubit, another qubit, another qubit, and all this cavity is just to couple to them. And here is just saying that the quantum state of this cavity. We are not using this one to do any computation. Yeah, so you're right. In principle, right? Can this be a 2 qubit? Yeah, you can implement it as 2 qubit, but then you need another layer to read it.
Okay, so
Yeah.
it's sort of like a trivial qubit that's there but not really want to care about it. That's the superconducting.
Yeah, correct. And when we do the manipulation, we don't manipulate this one. Whenever I say applying the quantum gates or whatever, we apply to this charge qubit. So this charge qubit is going to have another circuit to couple to it, and then we try to rotate it. And we are not able to manipulate the photon here. And yeah.
But it looks like we're manipulating it when it goes to the photon state, the one state, right?
Yeah, this is when you're reading it. You can say manipulation because you change it, but this is just because we apply a correct energy, then this one will be able to go to one photon because it's very natural, right? You have enough energy, then I just trap one more photon. And how much energy I need in order to trap one more photon depends on the qubit value. And then we can, from here, we deduce what the qubit is. Okay? Good question. Yeah, so don't get confused by this, okay? So let me go back, right? So then you will learn about this IQ block in the future. Basically, it is just a real and imaginary part with some transformation. But basically, as I said, right, if you are at the zero state, right, maybe this is clearer, look at this, right? If you are at the, let's say, zero state, the red one, and I measure at this frequency, you have this amount of imaginary versus this amount of real. For example, they are very close to each other, the two red, right? The red dot, red dash, and all the continuous line. But if it is one, it has this very large real and very rather small imaginary. You plot it as a real versus imaginary, they will be separated. Right? Think about this. Right? I can say, right, if this is real, this is imaginary. The red one, if I measure at that point, they might actually always, they might be around this point, right? They might be around this point. But then if I measure the real and the one state, the black one, then I might also have a similar imaginary, but I have a much larger real. Do you see that? And they are separated. If there's no noise, it's so easy to distinguish them, even they are very close. But if you have noise, you run into this situation, right? Because of noise, your block will just scattering. So the so-called fidelity is that how confident we are when we do the measurement, right? Because if we know they're separate, then we just draw a line. Whatever above, I call it 1. Whatever below, I call it 0 when I do the measurement. That's how I distinguish them. Okay? And this framework can be used to study if we reduce the power, then the noise, signal to noise ratio becomes smaller. You see the error will keep increasing. Okay, but that's not the main point of this class, so I will just stop here. Okay, any question regarding this brief overview of the hardware, just for superconductor? Yeah.
So why is it emergent each other?
Emergent because now the noise becomes large or your power becomes small. Then now, if you look at this figure, I start having a lot of noise. Then sometimes this can merge. For example, this black solid line will be very close to the black dashed line. Right? So at this point, we start moving to here. And once they merge, you cannot distinguish them. Yeah. Yeah.
Your thing reduce the pulse power makes it like more noisy.
Not more noisy, but more less resilience to noise. It's just like a regular signal communication, right? If your signal is smaller for the same amount of background noise, it becomes noisier, right? And that's why you need to speak louder, right, to increase your signal. That is same. reason. Okay.